Now we can work through molecular oxygen and all of its many possible molecular configurations that are nonetheless bound. So it gets kind of exciting, but first there's the simple bit. We've got the first four molecular orbitals are all sigma-type orbitals generated out of atomic s orbitals. So we have the sigma 1s, sigma star 1s, sigma 2s, and sigma star 2s. And those are pretty much always going to be the first four molecular orbitals. Now, those are generated, of course, by correlating out of the atomic orbitals 1s, 2s, and now we've got 2p hovering up here. So the next thing we're going to do is bring down the 2p z, the orbitals that are aligned along the bond axis, which is our z-axis here, and we're going to let those interact to form orbitals of type sigma and sigma star again, because again, these have zero angular momentum about the z-axis. And so even though they're made out of pz orbitals, the molecular orbitals are sigma and sigma star. Now, you should know that the full discussion of this involves some hybridization and other things that we'll get to in bits, but this basic picture works pretty well, and it works. It is certainly appropriate to molecular oxygen. So now I have the 2p plus or minus 1, or 2px, 2py orbitals here, and those are the guys that make the pi's. So the pi and pi star are the 2p x and y, or 2p plus and minus, where the z component of the orbital angular momentum about that bond axis is 1, plus or minus 1. So those guys are the pi and pi star orbitals. Again, it's important to note that for linear molecular orbitals, these are actually slinkies. So instead of having lobes with positive and negative sign, which is how we're used to generally thinking about them, which is indeed appropriate if we have a molecule of planar symmetry, like say ethene, for O2, for N2, for all the symmetric homonuclear diatomics, these pi and pi star orbitals actually have a slinky character going around the z-axis. So as we vary that angle, they go from plus 1 to I to minus 1 to minus I back to plus 1 as they zip around the axis. But they still have the general pi character, and in fact they have the general behavior that the symmetry is ungerade for the pi and gerade for the pi star orbitals there. So this is the atomic orbital overlap, the configurations that the interactions that lead to this basic molecular orbital diagram, which with some variance is the thing that plays everything out. So now we'll make, first of all, we'll populate the atomic orbitals down at 1s and 2s, and that doesn't do anything really interesting at all. Then we add 3 more electrons, all in different p orbitals, all spin aligned according to Hund's rules, and finally the 4th electron in the p orbitals for a p4 configuration, and that's O triplet p. And now we're going to have O triplet p interact with another O triplet p to make molecular oxygen. And really it's O plus O and 16 electrons. Just like with the Aufbau principle in putting electrons into atomic orbitals, we follow an Aufbau principle here, where we just have a pile of electrons and we want to fill them up in the lowest energy way possible. So we got 16 electrons here. We're going to toss the first few in. It's pretty straightforward. I put the first 4 electrons in. The first 2 go in the sigma. The next 2 go in the sigma star. And for the case of formalism, in case it isn't perfectly drilled into your heads here, the bond order of the system is the number of electrons in molecular orbitals minus the number of electrons in molecular orbitals with a star, so the number in bonding orbitals minus the number in non-bonding orbitals, and then we divide by 2 because it takes 2 electrons to make a bond. So far we've gone from bond order plus 1 back to 0, and the next 4 electrons take us up to plus 1 and back to 0 again. So we fill those S-type sigma orbitals with a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons, half of our electrons, and we've done nothing at all. In terms of the electrons, and the 2 oxygen nuclei don't like each other very much, and so we have absolutely done nothing to help our cause yet. Now, Well, we have shielded the electrons a fair bit, the nuclei a fair bit. I suppose that helps a tiny, tiny bit. So now we've got 4 more electrons. The next 2 go there in the sigma 2p orbital, and we get 2 more electrons. We've got 6 left, and our bond order now goes up to +1 because we have 2 more electrons in bonding orbitals. The next 2 orbitals, the next 2 electrons, according to Hund's rules, I'm going to put in opposite pi type orbitals, and I'm going to spin align them because I need to get that appropriate exchange symmetry so that the spatial exchange wave function for those 2 electrons is anti-symmetric. The spin exchange wave function is symmetrical, and that gives us the lowest possible kinetic energy for those electrons. So now I've got what we would call a triplet sigma term symbol. I'm not finished, but if we had stopped here, this would be a triplet sigma because the total orbital angular momentum of these 2 electrons is 0. They're going against each other. One's going one way around the system, one's going the other way around the system. They're plus and minus 1. So that adds to nothing. So the orbital angular momentum is 0. We use a capital sigma for the molecular orbital angular momentum about the z-axis because just like SPDF, this is sigma pi delta, and the capital indicates the total electron orbital angular momentum. But it's spin triplet because the spins of these 2 electrons are aligned in parallel. So this is exactly analogous to the atomic orbital total electron quantum numbers that we dealt with in the term symbols for atoms. There's absolutely no difference, just the orbitals look a little bit different. Well, I've still got a few more electrons, so we're going to put 2 more electrons in those pi bonding orbitals. That gets us up to 14 electrons and +3, triple bond. We've got a +3 bond order. I'm still not done though, because I have finally 2 more electrons that I have to shove up into this pi star. So those 2 are in a star orbital, so I've gone all the way up to +3 in my bond order, and I come back down to wind up with a bond order of +2. I had to stash the final 2 electrons in anti-bonding orbitals, so they do not help with the stability of this molecule. Now, they hurt, but they're still there, and they still, to get the minimum energy, I am still going to align the spins so that the spatial electron exchange wave function is anti-symmetrical. The spin electron exchange wave function is symmetrical. I get the overall anti-symmetry required with the exchange of electrons, but I do so in a manner that gives me the minimum total kinetic energy for this configuration of the atomic oxygen. The overall configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2p4, pi star 2p2. So that is the configuration, the orbitals that the numbers of electrons go in, but I've got these 2 aligned electrons. The total orbital angular momentum is still 0, so this thing comes out as a triplet sigma again. So triplet because of the spin degeneracy. The spin is 1, 2s plus 1 is 3. We got a triplet. Sigma because the total orbital angular momentum about the z-axis is 0. So oxygen triplet sigma is the ground state for oxygen. Now we can also look at excited term symbols, and it takes a little bit of thought. More or less what you have to do is look at the term symbols and try to figure out what was going on, but some of the molecular excitations are fairly straightforward. The pi star orbitals are the lowest energy orbitals I could stash those final 2 electrons in. So if I want to excite this system and maintain my bond order of 2, I can get rid of that electron in the right-hand pi star and move it over to the left-hand pi star. I have to anti-align the spins, which is bad for energy, and I also have to bring the electrons in the same orbital, so now they're going the same way around the electron and they have to do more work to avoid each other. To some extent they actually do essentially stay 180 degrees out of phase as they do that, but they can't do that completely. So the energy goes up for both reasons, because the spin is now of the wrong symmetry. I've got an anti-symmetrical spin exchange, which requires a symmetrical spatial exchange for those electrons. That's higher in kinetic energy. The electrons on average are somewhat closer together. That's worse. So this is a higher energy term for molecular oxygen. Now, the spins are, the total spin angular momentum for the electrons is 0, because all of these electrons are paired up, but I've got 2 electrons going in the same direction about the z-axis, each with individually 1 unit of orbital angular momentum about the z-axis. So m sub z is now 2, and that's SPD, that's delta, and it's capital delta because we're dealing with a total. So this is a singlet delta form of molecular oxygen. And singlet delta oxygen occurs. It exists. It's important in the upper atmosphere of the Earth. It is a product of some number of chemical reactions because of the molecular reactions. Chemical reactions require proper conservation of spin symmetry, so sometimes you have to give off singlet oxygen from a reaction. That will influence the overall thermochemistry of a reaction, because this is higher in energy than the triplet sigma form of oxygen. So we can keep playing this game a little bit. Let's get rid of that singlet delta, and now we can take the electron, one of the bonding electrons from that pi, and promote that up to back to the pi star, if you will. And this is now a triplet sigma, because I have no orbital angular momentum, but I have 2 aligned electrons. So there's a triplet sigma configuration sitting in there. Formally, the bond order is now 2, but in the end, it's really just a question of what different configurations have, or different total term symbols and configurations have lower energy. So we've gone now to a pi 3 pi star 3, clearly significantly higher in energy than the bound triplet sigma case for molecular oxygen, but it's another one. It's still bound. The bond order is now 1.5, but significantly higher in energy. We can get rid of that guy. Send that bonding electron back down into its happy place, and also envision another promotion, a second promotion for this brown electron. We'll get rid of that and send it on up to the sigma star, which is higher in energy still. And so the question of which of the 2 of these, I promoted a pi to pi star, and there's some energy gap there, and there's a pi star to sigma star energy gap there. And whichever one of those is a higher gap basically is going to wind up with the higher energy term symbol. But so now, again, I'm going to do this in the triplet spin configuration for the same old reason. I want a symmetrical exchange wave function for spin so that I can have anti-symmetrical exchange wave function for spatial exchange, and that has the lower kinetic energy. But now I have an electron with a pi, so a m sub z is of 1, and the extra electron has a sigma m sub z of 0, so my total m sub z, my total orbital angular momentum about the z-axis, is now just 1. And so this guy is a triplet pi configuration, which you can also find in the stack of term symbols for molecular oxygen. So that's essentially the way this works out. There are many different ways that the electrons can be emplaced, and each of those is a separate set of states. Each of those is a separate level. There is also spin-orbit interaction that we're not talking about very much at this point, but all of these things actually are bound forms of oxygen. In fact, this last one, this triplet pi we've wound up with here, it's got extra electrons wandering around in anti-bonding orbitals, but it still formally has a bond order of 2. So it's still very definitely bound stuff, though it's getting higher and higher in total energy.